Hi everyone. In the previous lectures, we discussed about capacitor circuits and capacitor circuits with DC inputs and some fixed inputs like step and impulses. And they were purely capacitive circuits. Eventually, we will go on to analyze circuits comprising of resistors, capacitors and inductors. And our aim is eventually to actually guess the outputs of those systems using simple intuitions without resorting to complex calculations. So this lecture is essentially intended to give you the basics necessary to follow what's presented in the next lectures. It's more like a brush up, so I won't be covering in depth of any of the concepts. It's just I've already assumed that you have taken a basic course on signals and systems and a basic course on control systems to be able to follow what I'm going to cover in the next few lectures. So here I'll just brush up the few concepts and just to draw some parallels between the time and frequency domain, and then just to brush up the concepts for you to follow the next the up and coming lectures. So first, I've just shown what I'm going to cover in the lecture. A little bit about Laplace transforms and starting with time domain response, and then I'll also cover a bit about frequency domain response. So first, consider a circuit like this with an input Vi and an output V0. So I'll apply KCL at this node. So then you can write C dV0 by dt equals Vi by V0, Vi minus V0 upon R. This can again be rewritten as now I'm going to call this term RC as tau. It's called time constant, which is dV0 by dt plus V0 equals Vi. Now this is a simple first order differential equation. Okay, there is a standard way of solving this. First we assume Vi is 0 and then solve this equation tau dV0 by dt plus V0 equals 0. The solution for this equation is V0 of t is V0 of 0 e power minus t upon tau. Now you can very easily see how do you get that is dV0 by t is V0 by tau. So the derivative of the signal is also proportional to the signal itself with a negative sign. The only function that satisfies that equation is an exponential and it's a decaying exponential. That's how you get the negative sign here. So the solution for that equation, when you apply a zero input, it's called natural response, is what I've shown here. Then you actually apply the input and find the response and add the two responses. Okay, I'm going to call V and 0 as the natural response, and similarly you have to find V of 0 as the forced response, and your final response of the system is sum of the two responses. Now we will find the input for a step response. So I'll apply a step of value 0 to Vx and find what is the output. So first, natural response is anyways given by this. Now we'll try to find the forced response, and again I'll not solve this equation. So this is a step input. I'm going to call it Vx into u of t. It's a step response, step function. Now when tau into this is the response for this is your equation for a step input. Again, there is a standard way of solving this problem. I'll quote the final result. Your forced response for this will be Vx or V0 of infinity. I'm going to write it as V0 of infinity. Instead of Vx, I'll call it as V0 of infinity. This is nothing but Vx into 1 minus e power minus t upon tau. Okay, this is into u of t. So the total response for the system V0 of t will be V0 of infinity into 1 minus e power minus t upon tau into u of t plus V0 of 0 e power minus t upon tau. Okay, I'll just ignore u of t for the time being, assuming all this the outputs are all starting from t equal to 0. I'm making that assumption. It's starting from t equal to 0. Now this equation can also be rewritten as V0 of infinity plus V0 of 0 minus V0 of infinity into e power minus t upon tau. So this tells you that if you take a first order system, the step input of a first order system, okay, if you know the final value and the initial value, you can exactly draw how the waveform will look like. It's very simple here. So I'll assume the system starts at t equal to 0. I'll plot the output here V0 of t. So first there are three possible conditions. V0 of infinity is less than V naught of 0. So your V naught of 0 is here and V naught of infinity is here. Okay. Now we know this term V naught 0 minus V naught infinity will eventually go to 0. The gap between these two will go to 0. Eventually the output will reach V naught of infinity, and this will respond like this. It's an exponential decay. It will decay down like this. Okay. Here I am assuming V naught of infinity is a large number. So this is the initial gap. I have shown it on this figure here. Eventually it will go to 0 and it will touch V naught of infinity. The other possibility is when V naught of infinity is greater than V naught of 0. So this is your V naught of infinity, and V naught of 0 starts here. Then your output, the gap between V naught of 0 and infinity is this. That will eventually go to 0, and output will eventually reach V naught of infinity. So the response will grow like this. This is actually 1 minus e power minus t upon tau. Now if I have the third condition, when V naught of 0 equals V naught of infinity, what exactly happens is this term goes to 0. So your V naught of t is simply equal to V naught of 0 or infinity. So when V naught of 0 and infinity are same, then your output just stays there. So that's what this function is telling you. So we have drawn for a first order system where it's very simple first order system. When I say a simple first order system, it is like this: tau dV naught by dt plus V naught equals Vi. A simple first order system. There are only three possible responses if you know the initial and output initial and final conditions and the time constant. Now we will tell you how to find the time constant in the coming lectures. I will tell you how to find for complex circuits, how to find it. I will tell you that. But now if you know the time constant, then you can very easily plot the outputs. Okay, and there are only three possible outputs which I have shown in this graphs. Okay, so I'll probably take that example here itself, or probably, yeah, I'll just I'll probably cover it in the next lecture, the examples for this using RC circuits. You might have to just remember these results. Probably for the first time it will look might be looking intimidating, I don't know, but in the next lecture it will become very simple. Once you analyze more and more problems, it will look very intuitive to you. Now as I add more and more RC circuits, what we did was simply analyze a first order RC circuit. Now if I start adding more and more RC circuits and I am interested in studying the behavior of the system, then it becomes very complicated. You will get an equation like this: nth derivative, I am assuming I am adding n capacitors here. There are n such RC sections. Okay, there are n such sections where each section is a simple RC circuit. You will get dV naught by dt power n, some coefficient alpha, till V naught equals Vi. Now to solve a nth order differential equation, as the order of the equation increases, the complexity of solving it also increases. Okay, so to how do we resolve this? Then if you have taken a basic course on signals and systems, you would know that we go for Laplace transforms. A Laplace transformation is actually for any signal x of t, for any function x of t, is given by e power minus st dt. Your x of s is given by this. Now by doing this transformation, you can actually convert linear differential equations to linear polynomial equations, and by solving those polynomials you can actually obtain the final time domain response in a very much easier manner than what it would take in a time domain, solving a time domain equation. So I'll just before I cover an example to prove what I just said just now, that it's easier to solve it in for Laplace transform, I'll just cover Laplace transforms of some very popular signals which will be useful throughout the series of lectures. So an impulse is a commonly used function. The Laplace transform of an impulse is 1. The Laplace transform of a step function is 1 by s, and Laplace transform for decaying exponential is 1 by s plus a. And similarly, if I have a function x of t with the Laplace transform x of s, then the differentiation of that function, the Laplace transform is x of s into s, and the integration of that function, for most of the functions it is x of s by s. There will be some additive terms depending upon the initial values and all that, but for most functions this is a valid equation. So knowing this, we'll actually try to solve a simple first order differential equation, which is tau dv naught by dt plus v naught equals vi. So I'll take Laplace transform on both the sides. You will get s tau plus 1 into v naught of s equals vi of s. Now the ratio, I'll write v naught of s as 1 by 1 plus s tau into vi of s. Now I'm going to apply a step input where with an output with a value of 0 to vx. So your v naught of s will be 1 by 1 plus s tau into vx by s. Again, this can be written using partial fractions as vx into 1 by s minus 1 by 1 plus s tau, and I have to multiply this by tau. Okay, I'll reduce it further as I'll take tau common outside. I'll get 1 by s plus 1 by tau. This is the equation you have for v naught. Now I'll take inverse Laplace transform of this equation. You will get v naught of t equals vx into u of t minus e power minus t by tau into u of t, which is vx into 1 minus e power minus t upon tau into u of t. And this is exactly what is the forced response of the system. Okay, so forced response of the system was very easily found by using this, and similarly we can also find the natural response by using a similar approach. So that is the main advantage of Laplace transforms. Now Laplace transforms make your analysis of complex differential equations, finding solutions of complex differential equations much easier. That's one of the main motivations for it. There is other reason is that if I find v naught of s by vi of s, I get a function h of s. So in this case it is actually 1 by 1 plus s tau. This function is called transfer function. Okay, now we can infer a lot about the system by just studying the transfer function. Okay, but if you have taken a basic course on any signals and systems, you would know that the Laplace transform, the transfer function blows up to infinity at some values of s, and those values are called poles, and it also goes to 0 at some values of s, and those values are called zeros. Okay, and also you know that if the transfer function has poles and those poles lie in the left of plane of the s domain, so this is called the s plane, and the real axis, and this is your imaginary axis. If your poles lie in the left of plane, then the system is said to be stable. If they lie in the right of plane, the system is said to be unstable. Now if your poles lie on the j omega axis, then the system is said to be marginally stable. It's also called oscillatory. Okay, it's called as marginally stable systems. Now by just looking at h of s, okay, when also h of s turns out to be, because most of the systems we analyze in circuits will be linear differential equations of higher and higher orders. It will actually be a polynomial it will actually contain a numerator polynomial and a denominator polynomial. Normally it will contain both polynomials in numerator and in denominator. Now by solving the denominator polynomials, I get the roots of a denominator polynomials, and those roots actually turn out to be poles, and the roots of the numerator polynomial turn out to be zeros. So I'll take a simple example. If you take dv naught by dt into tau plus v naught equals say dvi by dt into say 1 by omega z plus vi. Now take Laplace transform on both the sides. I will get s tau plus 1 into v naught of s equals 1 plus s by omega z of vi of s. Now the ratio v naught upon vi is 1 plus s by omega z by 1 plus s tau. Now the poles for the system, if I equate the denominator to 0, I will get s equal to minus 1 by tau. That's your pole. When s equals minus 1 by 2, this function actually blows up to infinity, and when s equals minus omega z, your function blows to 0. It eventually tends to 0, vanishes to 0. So I can here, if you can see, the transfer function can be represented as a polynomial as a numerator polynomial and a denominator polynomial. When you equate the denominator to 0, the roots of those equations, okay, are called poles. Okay, they are roots of it. The roots of this equation, denominator polynomial, are called poles. Now by just knowing those roots, you can actually predict a lot about the system. You can say whether the system is unstable or stable. Okay, if you feed in a step input, an unstable system will actually eventually grow to infinity. So for example, let's consider you have R and C, and I feed a step input to the system from 0 to say Vx volts. Initially I am assuming the capacitor voltage is 0. So what happens is that initially there is a current flowing in the circuit which is Vx upon R, Vx minus 0 by R, which is Vx by R. So your output will rise with an initial slope of Vx upon Rc. Now as the output increases, your current that is incoming into the capacitor reduces, because your current is given by Vx minus V0 of t by R. So as Vx increases, the current reduces. So as the current reduces, the slope of this input reduces, because your input is now charging, the charging current is reducing, so the charging voltage is also slowly incrementing. Eventually, when your voltage V0 reaches Vx, the current injecting into the capacitor will become 0. At that point onwards, your capacitor voltage will remain constant. Okay. So now here I have applied a bounded input, my output is also bounded. Such a system is called a stable system. Now we have just derived the transfer function for the system, it is 1 by 1 plus s tau. The poles of the system is minus 1 by tau. So here it is the pole on the s plane is at minus 1 by tau, so which is actually in the left of plane, so the system is stable. Now consider another system where I have a resistance of minus R, it's a negative resistance, and I am giving a step input of 0 to Vx volts. Now for this system, when I am trying to find the output voltage, this is your Vx. Initially output is 0. Now what's happening, you are actually drawing out current from the capacitor, or you are injecting a negative current into the capacitor of value minus Vx upon R. So your capacitor voltage will reduce because your current is being drawn out from the capacitor in this direction, right? The current value is minus Vx by R. Now Vx by minus R, so it's minus Vx by R. So you can also write it as the current as minus Vx minus V0 upon R. Now if your V0 is negative, this term will become, the overall current will become more and more negative. So eventually it will go to infinity. Okay, the output will eventually go to, the output will keep on increasing, reducing, and the current will also keep on increasing because it's flowing away from it. You can very easily show that. This term will always be positive, so minus of that will be always negative. So therefore your voltage will keep on ramping up. So the solution for this will be V0 of infinity into 1 minus e power minus tau, because your time constant is negative where it's minus Rc, this will be plus tau. So this function, if you see, if you start at 0, it starts at, when t equal to 0, this function is 0, so it starts at 0 here, and eventually when t is infinity, it goes to minus infinity. So it goes to minus infinity. Now the poles for this system, if I derive this system, it's actually, if I write the equation for this, it is 1 by 1 minus s tau, s equals 1 by tau, where tau equals Rc. Okay. So now you can see that the poles are in the right of plane for this system. It is actually 1 by tau, it is 1 by Rc. The pole is in the right of plane. So therefore this system is unstable. Now by just looking at the poles, you don't even have to feed any inputs to find whether it's unstable or not. By just looking at the poles, you could actually say the system is unstable. Okay. Now the next thing is, how do you find transfer function? We saw V0 by Vi is h of s. So V0 is simply h of s into V of I. All you need to do is just feed an impulse. We know the Fourier transform, the Laplace transform of an impulse is 1. When you feed an impulse, the output is simply going to be the transfer function itself. So that's how you find the transfer function. Okay. So this is the basics about Laplace transforms which you need to know, and now we will go to Fourier transforms. Now we know from basic Fourier series that any periodic signal can be represented as a linear combination of complex exponential or sinusoids, can be expressed as a linear combination of sinusoids. Okay, I am assuming the period of the sinusoid is t is given by 2 pi by omega naught. That's the time period of the x of t signal. For an aperiodic signal which is not periodic, you can represent it as a continuous, using a continuous function this is j2 pi ft dt. Okay, df. So this is your Fourier representation. So meaning I just have to forget about the signal and just remember another function called x of f, which contains all the information you need to know about x of t. And what it tells is, actually it tells you that any signal can be composed as a linear combination and as a function of sinusoids, and x of f is nothing but a bunch of, it's actually a set of complex numbers containing amplitudes and phases for different frequencies. Okay. Now how do you find x of f, or the Fourier transform of a system, I'm going to use a word called frequency response. So when I talked about Laplace transforms, I said h of s is called transfer function. Okay, we found by feeding an impulse. Now frequency response, when you substitute s equal to j omega, or you evaluate your Laplace transform along the j omega axis, you get Fourier transform. Again, this is a very loose statement. What do I mean by that is, every signal which has Laplace transform will not have Fourier transform, even it did not have. There are signals for which there is no Fourier transform, but there is a Laplace transform. Okay, so that has to be kept in mind. And frequency response is simply given by, sometimes you can simply substitute you can substitute s equal to j omega, and you would get what we call frequency response. It is the same thing explained in Fourier domain. Okay. Now why do we do frequency domain analysis? Is that it gives you a very interesting understanding of capacitors and RC circuits when we go for this frequency domain analysis. So what we do here is that we apply a sinusoid with fixed amplitude A, A cos omega naught t, assume the phase is 0, and then we measure this. This system can be a system composed of resistors, capacitors and inductors. Now the output of this system, see, understand this, again there is other term which you would know if you have taken a basic course on circuits, or on signals and systems or control systems. There is a term called linearity and time invariance. If a system is both linear and time invariant, a linear system is 1. If I increase my input by a certain factor x, output should also increase by the same factor. Okay. Now the time invariance says that if I shift my input by tau seconds, output should also get shifted by the same amount. That's what time invariance says. And also time invariance, that's a very mathematical definition. General definition is that you repeat the experiment any number of times, you will get the same output. You start the experiment at a certain amount of time, you get a certain output. You start the experiment tomorrow at the same time, you should get the same output. So that's invariant with respect to time. That's what it means. And as you apply a sinusoid, here the frequency is fixed. In LTI, linear time invariant systems also have another important interesting property, since by virtue of their linearity, if I apply an input signal of frequency omega naught, output will also contain only omega naught. It will not contain any other frequency. So for a linear time invariant system, the output cannot contain frequencies other than omega naught. Now this is a very important point. Now if your frequency is fixed, if I fix my input frequency, output frequency is also fixed. The only other variable is amplitude and phase. A of omega naught at that frequency and phase of omega naught. So as I vary omega naught, A of omega, I obtain a function A of omega naught, the amplitude and the phase. Now h of j omega, your frequency response is essentially A of omega naught e power j phi omega naught. It's essentially, it tells you, it contains information A omega, I'll use the word omega here because it's a frequency now instead of omega naught, e power j phi omega. Okay, I've just used omega here, and it's just frequency, the variable. I've just, instead of omega naught, I've used omega. It's just a frequency variable. So h of omega contains information. If I feed in a signal of certain frequency, you will know how much will that signal be attenuated from A, but by how much will it be shifted in phase. Okay, what is the quantity by which it will be shifted in phase. So both this information is contained in frequency response. Okay, again I discussed frequency response because it's very important. For example, if I take both frequency and Laplace transform, now that we have discussed it, I'll just quickly discuss why did we discuss it, where are we going to use it. So if I have a capacitor, a simple capacitor, see, assume current is the input, voltage is the output. Okay, or I can assume vice versa. I'll assume voltage as the input and voltage as the input and current as the output. And similarly, I take a resistor and apply a voltage and measure the current across it. Now we know the I is given by C dV by dt. Now if I take Laplace transform on both the sides, I'd get I of s equals C into SC into V of s. So V of s by I of s is called impedance, which is 1 by SC. And similarly, V of s for I of s for a resistor, I am going to call ZR of ZC of s. I of s for a resistor, ZR of s is going to be R. Okay, you can derive this with very simple equation. So from Laplace domain, we got ZC of s as 1 by SC, and the impedance of a resistor, I am using the word impedance, it's a complex resistance. Okay, if the resistance contains complex numbers, it becomes impedance. So ZC of s is your capacitive impedance, and the Laplace transform of the impedance of the capacitor is 1 by SC, and for a resistor it is constant. Now if I do a frequency analysis, okay, so I'm sorry, I'll just finish this discussion. So 1 by SC is your transfer function, impedance of capacitor. So if I have a capacitive circuit like this, to find the transfer function, I can just assume your capacitor as a resistor of value 1 by SC and analyze it. So the transfer function simply becomes 1 by SC by R plus 1 by SC, which is 1 by 1 plus SRC. Okay, we'll get the same transfer function if I write the differential equation and find it. We'll get the same transfer function, but here I'm using circuit analysis techniques to get the final transfer function because it's a circuits course mainly. So that's the advantage of going for Laplace transform. So we can very easily analyze a capacitor as just replace the capacitive impedance as an impedance of element of an impedance 1 by SC and get the transfer function. And once you have the transfer function, as I showed you before, you can actually predict the outputs of the systems, and you can also tell the behavior of the system for different kind of inputs. Okay, so that's the usage of applying Laplace transform to circuits. Next is Fourier transforms. What does Fourier transform tell you about a capacitor or about the circuits? So again, assume that I have applied an input V of t and I of t. We know I of t is C dV by dt. So now if I take Fourier transform on both the sides, your I of omega would be j omega into C into V of omega. Now I write I of omega by V of omega by I of omega. I'll call it ZC of omega, which is 1 by j omega C. And similarly, I can write for a resistance j omega of j r of omega is equal to R. Now here, by the Fourier transform actually captures the frequency dependence of the impedances. Okay, it tells you as a function of frequency, when I vary my frequency, how does the impedance of a capacitor change, or how does the impedance of a resistor change? For a resistor, it's always constant. The value is always R. For a capacitor, it has both, it's a complex number, so it has both magnitude and phase. I'll first plot only phase, only magnitude, so it will be a function like this. Okay, this is mod of ZC of omega. So what does this tell you? This graph tells you that at omega equal to 0, ZC of omega, the magnitude just blows up to infinity. At omega equal to infinity, the magnitude of the impedance blows up to, eventually reaches, vanishes to 0. Now, when an impedance is blowing up to infinity, it simply means that it's like an open circuit. So a capacitor, when you apply a DC input, it's going to behave like an open circuit. Constant input. When the input is very constant, it's said to be DC, unchanging. What is DC? DC is constant. It's unchanging. For a long time, if the input is unchanging, the system is said to be fed a DC input, and the capacitor will just behave like an open circuit. You can just open the two terminals and analyze the circuit. And for sudden changes, when there is an infinite frequency, your capacitor will behave like a short circuit because the impedance is 0. Now this has a very interesting thing in time domain. We just discussed this in time domain, that the voltage cannot change instantaneously. Now what has instantaneous change got to do with frequency? Again, I discussed this, probably I've deleted that video, but what I discussed is that if I assume a sinusoid of a signal like this, a cos a, let me just assume a sin omega naught t. So I'm going to plot this signal. The amplitude is a. Okay, it's a sine wave. Now I'll start increasing my frequency. I'll first reduce my frequency and increase it. If I reduce my frequency, it will be a slowly varying sine wave. If I increase my frequency, the sine wave will increase. This is increasing omega. Okay. Your omega naught is increasing here. I'll write it as omega naught increasing, okay, in this direction. As your omega naught increases, the slope at origin also increases. So that I'll find the slope at origin by differentiating this equation. You will get a omega naught cos omega naught t. So at t equal to 0, this reduces to a into omega naught. The slope is now dependent upon two parameters. One is a, other is omega naught. Now, if a is finite, but I make omega naught go to infinity, then what would happen is that this line, these frequencies would keep on eventually approach the y-axis itself. Okay. Suddenly, for an infinite frequency sinusoid, the line would simply look something like this. It would look like a constant line like this. Okay, a sudden step change. So why are we going for infinite frequencies is because we normally give step input as one of the most commonly given inputs in circuits. Okay, so when we give a sudden step input going from 0 to Vx, the system at t equal to 0 will think that an infinite frequency sinusoid has been fed to it at t equal to 0 alone. See, the step input has a combination, it's constant otherwise. It looks like a DC input here and it looks like a infinite frequency input at origin. So that's the interesting factor about step function. So at t equal to 0, a step function will look like an infinite frequency sinusoid. So therefore, a capacitor will behave like a short circuit the moment you apply a step. At t equal to 0, whenever you are applying a step input, the capacitor will suddenly behave like a short circuit. Okay, the capacitor will suddenly behave like a short circuit, and a resistor impedance is independent of frequency, it will remain the same. So that's the very important point to the takeaway point from this is that. So from frequency analysis, we concluded that when you apply a sudden step input, you should analyze your capacitor as a short circuit. Said otherwise, in time domain, the voltage across the capacitor cannot change suddenly. Okay, so a step input is a sudden change, so capacitor will suddenly act like a short circuit. So that's the outcome of this analysis. Okay, so we have discussed everything that we need to discuss about capacitors, Fourier transforms, and what we need to get out of it through what we need to actually take home from the analysis. Okay, which will be useful in analyzing capacitor and resistor circuits. Okay, I have discussed it now. Now I'll just mention one more final point, which is called phasors. Okay, now phasors we will not be using in our analysis. I'll tell you what phasors are. So sometimes in some systems the input frequency is fixed. I am not changing the input frequency. The only thing I'll change is the amplitude of the input. The frequency is normally fixed, which means I'm applying only a single frequency to the system. For example, sinusoids. Okay, again this can be resistor, capacitors and inductors. In such cases, as I said, a sinusoid is uniquely defined by three parameters: amplitude, frequency and phase. Okay, there are three parameters that determine them. Now once you fix omega naught, okay, there is omega naught is no longer varied. See, in Fourier transform frequency response, we varied even omega naught. Okay, but once I fix omega naught, in this case for a sinusoid, omega naught is fixed. There are only two parameters, a and phi. Now how does your all you need to worry about is how does your a change and how does your phi change. Okay, in that case I'll analyze my whole circuit entirely in the complex domain itself. So if I feed in my input with a zero phase, my output might have a certain amplitude and phase with respect to the input. Okay, and that can be shown in a diagram purely on a complex plane, and that representation is called phasor representation. The frequency information is hidden. We don't show omega naught because it's a single frequency system. Okay, that information is not shown. We only show the amplitude and the phase at the output with respect to the input. Okay, so such a representation is called phasor representation, and phasor representations find applications in power systems, because normally in power systems you apply a single frequency source like 50 Hz or 60 Hz. Okay, when analyzing a system, power systems where power is transferred for long distances, we use phasor analysis in power electronics and power systems. and also it is used in narrowband communications. When the bandwidth of the signal is so small compared to the center frequency of the carrier, in such systems we can approximate it to be nearly a single frequency signal, and there again we can apply phasor analysis. But phasor analysis doesn't find applications in signal processing where a certain band of frequencies are of interest. Okay, and even in our analysis of circuits we will not be using phasors, but it's applied in that in those analysis. Again, this is a very basic point. So again, I would recommend you to read any textbook on phasor analysis. I mean, like for example, I'll just say it in words. I'll just write the final things. If I apply a voltage with a peak amplitude Vp for a capacitor, the frequency of sinusoid is fixed, assume omega naught is the frequency, then the current is simply given by j omega naught V peak into C. The value of the current will be, the magnitude will be omega naught C into V peak. Okay, assuming a zero phase sinusoid is applied, the current in a capacitor is given by j omega naught. So j is a complex number, this is a complex plane. Okay, Vp is 0 here. So here current is said to lead the capacitor voltage. For a resistor, both the current and voltage will always be in phase. Okay, if you apply the same frequency. And for inductor, the current will lag the voltage. I will discuss about inductors much later. Okay, I will stop at this point. In the next lecture, we will cover extensively about problems on RC circuits. Thank you.